Hey guys, welcome back to lesson number 8. So we are continuing where we left off. On Monday we talked about Le Chancelier's principle. We did that for about 3 days total. So here we are moving on to the last topic in unit 9, and that is entropy. Now the work that you have due today, I know it's not on the screen, but you have the reading on entropy, then you have a Google form on entropy, just a little practice, and then you have about 5 regions questions on that as well. So no big issue. If you have any problems with the softwares, please let me know. I think I was setting some of them up too quickly that it didn't allow you to have access to it. So I think that should be fixed now, but if you do have problems, let me know. So entropy. First of all, we need to talk about what is entropy. Entropy is the degree of randomness or chaos or disorder in a system. I like to call it the messiness in a system, the messiness of particles in a system. That is what entropy is. So the messier it is, the more entropy you have. So we want to be random, we want to be chaotic, we want disorder. That is what entropy is. Now, nature tends to proceed to a state of greater entropy, below entropy. Meaning, I want more disorder but I want less energy. I want more disorder and less energy, or low speed or low rate. I want that all to happen. So I want more disorder because remember, the more disorder you have, the more collisions you could have, and the more collisions you can have, the faster your reaction will go to completion. So we want more entropy. Like I said, the more entropy you have, the less the less entropy you have. Sorry, the more order you have, the less entropy you have. The less order you have, the more entropy you have. So we can go ahead and determine this 3 ways. And we can determine how much entropy we have in a chemical reaction. 3 ways. The first way is by looking at the phase changes. The second way is by looking at the the chemical reaction itself. Do we have a decomposition reaction? Are we seeing our molecule break up into particles or atoms? Or are we seeing them come together to form compounds? And then the third way, which if the other 2 way doesn't work, you can use the third way, and you can determine using the number of coefficients or the number of molecules from reactants to products to determine if you have more entropy or less entropy. So let's go ahead and work through each one. So, determining the entropy based on phase change. Now, as we look at a solid particle here, and the solid particles here, and then a liquid particle and a gas particle, we have more order in the solid because all our particles in a solid are stuck together. It's a rigid structure. The particles are not moving anywhere. They're packed together. So we have more order here than we do in a liquid particles, because liquid particles are free flowing liquid particles are free flowing, meaning they are able to go anywhere they want to based on the object that they're in. So they can't flow out, but based on the object they're in, they have the ability to move around. So we have a little bit of disorder here. And then we have our greatest disorder when we have gas particles, because gas particles are able to flow either which direction they want to. Even if they're stuck or put into a container, they're able to move around. You currently have gas particles all around you, and they're free flowing. They're able to go wherever they want to. But ice particles or ice, the particles in ice can't go anywhere, right? They're stuck together. They're stuck in a rigid structure. So as we go from solid to liquid to gas, our entropy is increasing. We have an increase in entropy. Entropy can also be written as delta S, right? So we have an increase in entropy. Delta S means entropy. So we have an increase in entropy as we go from solid to liquid to gas. Now, entropy based on bonds. Entropy increases when bonds are broken. Entropy decreases when bonds are created. Think about it this way. When you're creating a bond, you're forcing the molecules that are randomly all over the place to come together. So they're becoming more organized. But when you break a bond in a compound, the molecules that were stuck together are now able to free flow. They're able to go wherever they want to. So thus, when you break a bond, you have less order, right? And then when you create a bond, you have more order. It's more organized. Right? So, bonds are broken, you have less order, more entropy. But when bonds are created, you have more order. So, you have less, sorry. You have less when you, sorry about that. When bonds are broken, you have less order, more entropy. But when bonds are created, you have more order, less entropy, right? Because your molecules are now coming together instead of being apart. So, the reason why, and this reason why also takes me back to something that we did previously. So, bonds making versus bond breaking. When energy exits the molecules, we are able to go ahead and create bonds. So when bonds are actually forming, they're releasing energy, as this picture dictates. However, when bonds are breaking, they are taking energy in. We need energy to go in to pull the molecules apart. But the energy in which the molecules collide with each other is released when they form. So then we have this acronym, BARF. So when we break bonds, we absorb energy. But when we release energy, we form bonds. That's where this BARF comes from. Alright? Just wanted to take that back for a quick second because I know that a couple of us were like, what does BARF mean? That's what BARF means. That's what that acronym means. Alright, and the last part, entropy, determining entropy based on molecules. Use this only if there's not a phase change, right? So if the number of coefficients decreases from left to right, reactants to products, your entropy decreases. But if the number of coefficients increase from left to right, reactants to products once again, your entropy increases. That's basically saying the less molecules you have, the less entropy you have. You have less molecules means more order. But if you have more molecules, you have more entropy because more molecule means they're able to move around more freely. All right. So let's do a couple of practice problems and then you guys are good to go. So, practice number 1, right? So we're going to do practice number 1 all 3 ways so you understand what I'm talking about. So for practice number 1, we're going from a solid to a solid and a gas. So we went from a solid to a gas. So our entropy is increasing that way. We are going from less order, we're going from more order to less order. So entropy is increasing. So we figured out that way. So entropy delta S increases, let's say. All right. Then we look over here. Let's look at it one more time. We have this KClO3 is a big molecule, right? And then when we go to the product side, we see that it broke up into KCl and O2. So that means we're breaking up. When a bond breaks, remember, when the bond is breaking, we have an increase in entropy. So that also verifies my answer over here, right? And then if we look at the subscripts, the coefficients. So if we look at the coefficients, we have a 2 over here, right? So on reactor side we have 2, but then on the product side we have 2 and a 3, so that's 5. So we're going from 2 to 5. So we have an increase in our molecules. So if we have an increase in our molecule, our entropy once again is increasing. All right. So number 2, H2O liquid to H2O solid. Right? We're going from a liquid to a solid. That means our entropy is decreasing because we're becoming more rigid in our solid structure. Then number 3, let's do the phase change first. We have gas, gas, and gas. So we can't use phase change to help us with this. So let's go to the second one. Is this being, sorry about that. So if we look over here, we have gas, gas, and we have gas, gas, and gas. So we can use phase change to help us. But over here, we are seeing that N2 and H2 are combining to give us NH3. So is the bond breaking or being created? The bond is being created, and because the bond is being created, that means that our entropy goes ahead and it decreases. Number 4, we have NaCl solid, so we have a solid here. Then it goes to aqueous and aqueous. Once again, aqueous means that it's been mixed in with water. It's dissolved in water. So we're going from solid to an aqueous solution, which is basically a liquid. So our entropy has gone ahead and it's increasing, right? And then over here, for number 5, we are going from a solid, from KCl solid to KCl liquid. So we're going from solid to liquid. We're becoming less organized, more random. So our entropy is going ahead and it's going to go ahead and increase. I forgot to put my delta S's here to tell you that I'm talking about entropy. So let me go back and put that in. But once again, as I'm putting this in, remember, there are 3 ways to determine entropy based on phase change. As we go from solid, liquid to gas, our entropy is increasing. The second way to determine entropy is determining if the equation is showing, if the bonds are either breaking or forming. If the bond is breaking, you have more entropy. If the bond is forming, you have less entropy. And the last way to determine entropy, if you cannot use the other 2, is to determine the molecules. Is the molecules increasing from left to right? Then your entropy increases. But if your molecule is decreasing from left to right, then your entropy decreases. If you have any questions, please let me know. I am here to help you. And have a great day. Practice this out. All right? See you guys later.